learning, but I'm just in general interested and like a hobbyist practitioner. Okay, so we can get started.
Yeah. Maybe you can just do your microphone.
A bit higher.
Yeah.
Here.
Yeah, fine.
All right. Okay. What is machine learning? Anyone? What is machine learning? Anyone wants to take a guess?
See how an algorithm can detect patterns in data.
Yeah, essentially that is it. Like machine learning is essentially detecting hidden patterns in data and then using those patterns to predict something new, right? So how many types of machine learning algorithms are there? Anyone? So mostly people say like 3 types: supervised, unsupervised, and reinforcement learning. These are mostly like major 3 types, and you have other types like semi-supervised learning, a recommendation system, active learning, weak learning. There are like lots of different sub-variants. So yeah, we'll not get into that. What we'll cover today is supervised machine learning. So what is supervised machine learning? Anyone?
You know the answer already.
I know the answer.
No, that's when you know the answer that you're trying to get.
Sorry. Classification. Yeah, so classification can be both supervised and unsupervised. It doesn't necessarily have to be supervised.
It just means that you have some data that has that you have the correct answer for what the right regression or the right class is, and it's whether it's classification or regression or whatever other class. And then you have some data that's not classified yet or labeled yet, and then you can use the data that is labeled to then test on the data, to learn on the data that's not labeled.
Yes. So yes. So supervised learning is when there is a supervisory signal is available. So from the supervisory signal, you can learn some pattern, and using that pattern, you can predict something in future or anything that is not labeled yet. So in supervised learning, we usually call it training data. Sometimes we call it what else? Sorry, we mostly call it training data. Sometimes we usually call it like label data, but training data is the most common form. And then the question is, what is unsupervised learning? So, yeah, we have the data, but there is no label to it, right? So, for example, in Titanic, in the data set we'll be dealing with today, Titanic. So the problem is you have all these different attributes of the passengers, and you have to predict whether that particular passenger has survived or not, right? So if we know the information whether that particular passenger has survived or not, if we know that information, that will be supervised, because we have the supervisory signal. We know it's labeled whether someone has survived or not. But if there is no such information available, then it will be unsupervised, because there is no available label that whether someone has survived or not. And there is another type of learning called semi-supervised. So semi-supervised is something in between. For some training data, you have labels. For some training data, you don't have any label. So you kind of impart the label from other training data. So that's called semi-supervised. But we'll not get into that. So there are like 2 major types of supervised learning algorithms. One is classification. The other is regression. So what is classification? So classification is just trying to predict. You have some training data, and you are just trying to predict what class this training data or this data belong to, right? So if you have if you have an email, trying to predict whether this email is a spam or not. Now you have like 2 different categories, right? 2 different classes. One is it can be a spam. Other is it's not a spam. So when you're trying to classify whether an email is spam or not, this is a classification problem. And what is regression problem? What is regression? Anyone? Yes, in a sense. So, so in classification problems, we are trying to predict different classes, right? So that means there is a finite categories, and we'll try to predict one of them. In regression, the output is actually not categories. The output is just a real number, like a numerical number, right? So for example, if you're trying to predict stock prices, that will be a regression problem. Because based on the historical data, you are trying to now predict what the stock price will be tomorrow. And stock price can be anything. It can be $1 billion, it can be zero, right? So that's a regression problem. So the problem we'll try right now is Titanic. So are all of you aware of this problem? Did you guys look at the data set?
Did people get the opportunity to download the data set from the email and from the link? Okay.
Okay. Yes, so yeah, Titanic is simply whether we have all the attributes of passengers like age, their gender, their name, whether their class, different types of attribute, and based on these attributes, we have to predict whether that person has survived or not. So that's essentially what Titanic problem is. Have you downloaded the data, training and test both? Okay. Okay, so before we go into that, just a little bit of theory. So what most machine learning algorithm works is sorry, I'm not very well prepared. We are trying to meet a deadline. Yeah, I'm sorry about that. Anyway. Okay, so most of the machine learning works like this. So you can think of this as 2 dimensions, right? We have 2 dimensions, X and Y. And this is a vector space, Euclidean space. So you will have some points in this Euclidean space. So every single point in this Euclidean space we'll call it training data. So I have one point in here, another point in here, and these are labels, right? So let's say anything with circles are not spam. Anything represented by a cross is spam. And we are representing every single training data in Euclidean space. That means these are all numbers. These are all vectors, right? So what a machine learning algorithm tries to do, it tries to find a separating function or a separating line or boundary that separates 2 different classes, right? So if this is a line, that means we call it a linear classifier. This is what we call decision boundary or decision function. And if this is linear, that means this is a linear classifier, right? What happens if we have something like this? Can I have a line that can separate these classes? Is it possible? No. Yeah, it's not going to be possible. So for those kind of problems, you cannot use linear classifier. The linear classifier is you'll always get something wrong. I mean, no matter what machine learning algorithm you're going to be using, you'll always get something wrong. But in this case, it's never possible to find actually a boundary, right? If you have a boundary like this, no, right? If you have something like this also doesn't work. But if you have something like this, if you have a machine learning algorithm that can have a decision boundary like this, then it can identify, it can correctly classify these 2 different kind of problems. So this is usually called nonlinear classifier. and there are like so many nonlinear classifiers out there. But anyway, now the question is, linear classifier looks very simple, right? Now, why do we deal with linear classifiers? Because linear classifier is, I mean, the limitation of linear classifier is very evident, right? It can only work for problems where you can separate different classes with a line, right? But now the question is why linear classifiers are like one of the most popular algorithms out there. Why? So the reason is, for most of the real life problems that you will encounter, linear classifier actually goes a long way. Yeah, it actually goes a long way. So that's one of the reasons. That's one, and the other reason is linear classifier is very easily interpretable. So interpretable machine learning is a huge research topic, and a lot of the state-of-the-art algorithms we are using right now are actually not very interpretable. So that's a huge problem, because we are going to be using machine learning like in so many different areas that this is going to affect our lives, and we need to know why a machine is making a decision and what's the reason that a machine is making this decision, right? If you cannot interpret a model, if you cannot interpret an algorithm, then there's not much thing we can do. Okay, so let's get back to coding now. So first thing first, we'll import scikit-learn. Everyone has all the dependencies installed. Okay, so you need scikit-learn, you need pandas, you need scikit-learn, pandas. Yeah, mostly these are the three packages you need, and also we'll use the site called Dive. Yeah, it's a really neat site. You go into that. Actually. So I already have dataset uploaded, but what you can do, you can go to upload new dataset, and you can just upload the training data from your computer. Yeah, so this is use dive.com. Yes. So this is our website.
The Titanic training that we're recording?
Yes. Okay, everyone?
Yeah.
Okay, let's go back. Do you see this visualization? You can go to the data set and click on this icon. You can see the visualization.
Where are you? Where are you clicking? Where's your mouse?
There.
Uh-oh.
Everyone? Okay, so the reason we are using this, because a lot of the first step of anything related to machine learning is you have to do exploration. We call it exploratory data analysis. So it's just trying to understand the data that you'll train your machine learning algorithm, right? So Okay, how many columns are there? 12 columns. How many rows? Almost 900. ID is the ID field. Okay, so it already identified the ID field. We don't have to do anything. Survived. This is survived column, right? So I think at first it identifies an integer, but you have to set it to Boolean because this is actually a Boolean value, right? Same with P class, passenger class. Same, this is an integer. Then you have name. Then you have gender. So you can also set it to Boolean. And then you have age. Then CBSP, it's like sibling and spouse. PARC is parent and child. Then this is I think ticket, and fare is fare. Kevin is Kevin number, and then embarked. I'm not sure exactly what this is, but anyway. So first thing, what we'll do, we'll try to find that whether all the data are there or not, right? So if you look at age, we see there's missing data. Yeah. So in age, there's a lot of missing data, and this will create an issue because a lot of machine learning algorithms cannot deal with missing data. So we have to do something about this. That's one. Is there any other columns we have missing data? In ticket, we also have missing data in ticket. Yes, so, okay, let's try to take, what do I have? Try to take it. Okay, so how many columns we have missing data?
Do we need to open the document?
Oh no, this is just for my note taking.
Okay.
We have age. Okay. What else? Ticket. What else? Kevin. Embark. Do we have missing data in Embark? Yes, there are 2 missing data. So usually when you see null means missing data. So okay, we have missing data in Embark. So yeah, most of the people didn't survive. You survived. Now we'll try to explore the relationship between different features, right? So feature is anything that's not our label. So survive is our label, right? And anything other than label, we usually call it features, right? So P class is a feature, name is a feature, sex is a feature. So let's try to visualize it. So if you go there, if you look at the distribution, let's look at the distribution of where. So this is the distribution of where, right? Let's look at that. We have few values that are very, very large. Right? So most of the values are like around $100 or less than $100, maybe $150. But we have some values that are almost 500. So now we have to make a decision. This is called outlier. Now you have to make. First you have to go to visualize. Click on visualize. Then you see all these distributions, right? Distributions of different features. So from there, what are you interested in? We're interested in where is fair? Okay, sorry. Yes. So this is the distribution of fair, right? And if you look at that, this looks normal, right? Most of the values looks normal, but there are 3 values that are like huge. Right? Those are like around 500. So now you have to make a call whether this is an outlier or not. So the issue with outliers that most of the time outliers are actually data, wrong data. And how can wrong data in your training data, how can wrong data can happen? Any idea? Yeah, it can, right? But how can this happen? Yes, you can have a typo, right? Like when you're entering something, you can have a typo. So this is another thing. You have to make sure that you are filtering out all the outliers. And once something is an outlier or not, there's no right answer to it. It just depends on your domain knowledge. If you are very, yeah, so it might be that I'm making the assumption this is an outlier, but it might not be an outlier. So I don't know. We don't know whether it can be outlier or not. So anyway, let's make a note out of it. An outlier. Fair. We have outliers in the column. Okay, let's go back to explore. And this looks okay. This looks sensible. So most of the passengers are from third class. Then you have some first class. You have some second class. This looks sensible. Yeah, I know this is very boring work, but trust me, most of the machine learning work is actually just exploring the data. It's not writing some super cool algorithm. It's not. Okay, where else? Kevin. So Kevin is one of the features is very hard to interpret because just by looking at the number, it's not obvious what you can make out of it. So I don't know how to interpret this, but one way to interpret this, you can see any Kevin that starts with A, maybe first class. Any Kevin that starts with C, maybe third class, or any Kevin that starts with F, it's a third class. So we don't have the data. So right now, what we'll probably do, we'll probably drop this feature because we don't know how to interpret this. So we'll probably just drop this. We're probably not going to do anything. There's one. The other distribution of age. So is there any outlier? Probably not. The max value is 80. So this is reasonable. 80 years old, this is reasonable. So yeah, there is no outlier, you can say. Okay, so this looks good. Now we'll try to explore the relationship between different features and how they interact with our labels. So yeah, go to analyze. Click on this icon. I'm sorry, this is very small. Okay. Everyone? Okay, so we're trying to see the relationship between survived and gender. Can we see any relationship? What do you know about Titanic? If someone is female, is she more likely to survive or not? Yes, we know that, right? Does the data set reflect that? This is called data validation, right? You have some domain knowledge. Now you have to make sure that whatever data you have actually follow that. So 0 means did not survive. 1 means survive, right? So we can actually see that there is a clear pattern here. If someone is a female, that person most likely survived. Okay, so far it's good. What else? Let's look at the relationship between fair and survived. So before going into that, do we know if someone pays like really high fare, that person is more likely to survive or not? Yes, that person is more likely to survive, right? Let's see. Let's see the relationship. So if you go down, yes, so that's like 3 to 1. On the other hand, the people who actually paid like really, really low fare, they're most likely to die. But if you go below like here, your chance improves, but not a lot. So this column, this feature fare, will still be useful. Let's look at the class. You see now there is a clear relationship. So people from third class obviously didn't survive much, but if you look at first class, okay, this is kind of weird. So people from second class actually survived more than first class. Okay, so I'm not sure what to make out of it because this kind of goes against our knowledge, what we know already, but this still might be valid because there are a lot of other factors are into play, right? Let's look at the age. So we know children and women fast, right? So if someone is a child, that person most likely survived. Does our data reflect that? You know, it actually does. If you look at here, if someone is almost 5 years old, they most likely survive. And the older you get, the chance of survival goes down. So this is also useful. What about sibling or spouse? So if someone has a sibling, that person has higher chance of surviving. Do you know why? Yes, but you can also get on live board if you have a younger sibling, right? So yeah, that's what's going on here. Just because you have a younger sibling, you got to get on a live board. Oh, okay. Yeah, sorry. Okay, I'll try to go into that. The same with parent and child. So if you have a child, that means you are more likely to survive. Same. Ticket. So ticket is one of the features. You can also look at that. So yeah. I'm not sure exactly. So where, I'm not sure what exactly is ticket. It's not quantity. Anyway, let's get into coding. Enough talk. So one good thing about pandas that you can read data directly from internet. Okay. So we'll just look at pandas. Is it your number? You can look at that. So you can see that age has missing value, right? You can see most of the data in Kevin.
We go back to the loading of the data.
Oh, sorry. It's a training data, so you can read it from your local machine. It just, I'm reading it from the internet.
It was linked also to email and the event issue. There. You can
Okay. Yes. So this is just like having a look at the data, so you can see what data is out there. df.add. Okay. Yeah. So you can see Kevin. Most of the data in Kevin column is missing. That means this is almost useless. We cannot use it. So this is one of those columns we need to drop. What about age? So age also has a lot of missing data. It's almost 20% missing data. So what we can do, we can drop this column. That means we are not going to use this feature. That's one option. The second option is we can remove the training examples that have age missing. We can remove those rows, or we can try to compute, we can try to make a guess what age looks like. So the first thing we'll do, this is called imputation. So imputation usually means that how you fill in the missing data, right? So for example, if you have age missing, you can just take the average of other age and just fill in with that. So in scikit-learn, you have sorry, I think this is in impute. Simple imputer. Okay. Then you can create a mapper. It's called data frame mapper. So what data frame mapper looks like is this. It's a list. First, it actually takes a list of a list. So for each column, we'll specify what kind of transformation, what kind of operation we want to do. So for age, what do we want to do? Simple imputer. And what simple imputer takes, it takes a strategy parameter, and in strategy parameter, you can say what kind of strategy you want to adopt. So you can say something, I think mean. So mean means it will fill in the missing values with the average of other values. And you can also say df underscore true. I think, yeah, that's the output. Then, so we just declared a mapper. We haven't performed any computation on our data yet. So let's do a perfect transform. Let's say let me see the syntax. I'm sorry. I don't know the syntax. Oh, it takes. Sorry. Oh, yeah, it takes a list. So what data frame mapper takes, it takes a feature name or a column name, and then the list of transformation, which is scikit-learn transformation you want to compute. And this is just something other parameters you need to pass on. If you don't want to, you can just leave it out. But sometimes I saw it throws exception. There's some bug out there, so that's why I just put it in. And df out true is it will output another data frame. So you can, let's just call it train. So now we'll look at train.info. So, okay. So what happened? So mapper feed and transform. So mapper has any scikit-learn algorithm usually have three different things. You have feed, you have transform, you have feed underscore transform, and you have predict. So what feed does, feed is essentially training. So if you call feed, it essentially trains. What transform does is based on the input, it will actually give you an output. So feed doesn't give you any output, it just trains the model, right? And transform actually changes your input. Feed transform is actually feed plus transform. This is just a utility method. Then you have predict. So predict is when you have trained a model, you just want to predict something. So if you look at here, now we don't have any null value. Well, we have 891 rows, and all of the rows are there. So there's no null value. That means that simple imputer actually computed other values. So that's for age. What else? We have sex, right? So we have to do feature transformation. So the sex was male and female, right? But what we have looked at, that a machine learning algorithm only deals with a number. So there has to be a way that you can change sex to a number. How can we do that? Yeah, so we can change. We can represent male with 0, female with 1, but this is not a good idea. Do you know why? So the reason is 0 and 1 are actually integers, right? They're number. That means there is a relationship between two. 0 is less than 1. So when you are putting that into an Euclidean space, that means you're also saying there's an order between them, but there is no order between male and female, right? That's one problem. And second issue is you're also saying that there is actually a distance between 0 and 1, because in Euclidean space, you actually have a distance between 0 and 1, right? But in real life, there is no such thing as distance. So you cannot do that. So how we can represent sex, right? So the way we represent sex is called one-hot encoding. So one-hot encoding is if a feature has n different categories, then you will have, with one-hot encoding, you will have now n different features for that particular feature. So for example, if you have a male, if you have a sex, this is the column, right? This is the feature. So now you will have two different features like this. And if someone is a male, that means there will be a 1. And if someone is a female, there will be a 0. And vice versa. If someone is a female, in male column, there will be 0. In female column, there will be 1. So this is called one-hot encoding. So we have to, what do we have to do? We have to do one-hot encoding. So in scikit-learn, scikit-learn dot pre-processing, yes, yes, one-hot encoder.
What does one-hot encoder mean? Where does that name come from?
One-hot encoding, because there's only one column that can be hot, right? Hot means 1. That's why.
So you're everywhere else in the world.
Yeah. So that's why it's a one-hot encoding.
Does this need to be a list, or is that okay with
That's a good question. I don't know. Yeah, it probably has to be a list. I'm actually not sure exactly when something has to be a list and something has to be not. I'm not too familiar with the API. Sorry about that. Yeah, let's do that. See, now we actually have two different features for sex. Same. We need to do same. Is there any other features like that? Probably not. Oh, we also have this embarked. So the good thing about this, you can specify all in here. Okay. What did it say? Yes. I don't know. Yeah. The engineering with this.
the square for the section part?
Why this is running an error? Good question. Input context not a number. You see what happened? So there are some missing values in Ember, right? And now we actually haven't done anything for that. So we actually have to do something. So we can do something similar. We can do imputation. But the question is, what do we do for that? In Ember, there is only 2 missing values. So one thing we can do, we can just remove those 2 missing values. So if it's very few missing values, you can just remove those rows. I mean, both are valid approaches. You can impute them like we did for age, or we can just remove those rows. Both are valid. Both are valid. I mean, I don't know which one is appropriate for which situation. It depends on your situation. Sorry, I'll just copy paste. I'm sorry. So what I'll do, this is, so this is a pandas method. What I will do, you give it a column names based, and it will remove any rows from that, any rows that are null in that column. So we are removing any rows that has null values in Ember. Okay. Sorry. Call it a string. Let's do it here. If you look at train.info, there are 2 null values, so those are removed. And you have now 3 different features. Okay. Where else? So the second thing you have to do is called scaling. So scaling is most of the machine learning algorithms, you have this requirement that every feature has to have 0 mean and unit variance. Do you know why? Why does every feature have to have 0 mean and unit variance? Sorry.
So our algorithm is not biased by the ones that have large.
Yeah, so some feature will naturally have very large values, right? Some feature will have like very small values. So you want to scale them so the algorithm doesn't put too much importance on features that have very large values, right? So we call it standard scaler. I think it's in pre-processing. Yes, it's in pre-processing. And we have to do this for anything that's numerical. So yes, you can actually have multiple transformers. We have age. What are the numerical columns we have? We have fair, right? Okay, let's do it. Let's also do it for fair.
So straight to 7 p.m. So I think we're going to get ready to leave right now.
Okay. Okay, we have scale. Yes. So we have fair. Is there any other? Let's look at that. Hamburg, ticket. No fair. We can do the same thing for sibling and parent, child. Okay, let's do the same thing for sibling and parent, child. Let's see. Okay, is there anything you're missing? P class. Okay, we also have another. It's called P class. Let's do P class. Let's do 140 import. Everyone. Okay. Okay, so this is more or less, we have done all the feature transformations. We are ready for our machine learning algorithm. So, but the question is, this is actually a data frame, right? And scikit-learn actually takes an array of real numbers, right? So we have to modify it to actually output not a data frame, actually a real number. So one thing we can do, we can just copy paste it. What we'll do, if you remove this will actually yes, this will actually return an array. Just remove this df out. True.
But the default.
Yeah, that's the default. That's the default. Yeah, that's the default. It's good if you when you're learning, it's good, and if you also want to debug, you want to see. So yes, so now this is actually ready for our machine learning algorithm. So let's try this. What kind of machine learning algorithm we have said we'll try? We'll try linear. So let's say where is this linear? Regression. Yes. Learn.linear model.logistic regression. Why doesn't it? Okay. Okay, yes, this is logistic regression. So what we have learned about logistic regression, we will instantiate an object of logistic regression with LR. What we'll do, we'll call LR.fit. What fit methods usually do, they usually train, right? So let's train it. LR.fit. What was our array? Our array was named train. So if you notice in our array, we only have just the features, right? But we also need to provide it the training, the actual training signal or actual labels, right? So how do we do it? df, if you want to access it like this, df survived. So we also, so the error is we actually removed some of the rows in here, but we haven't removed those rows from our df. So we actually have to remove those rows. Okay, we have trained our model. So now we can see the prediction. Predict. We are on board. So this is our prediction. 0 means did not survive, 1 means survived, and we are predicting on training data. What's wrong with that? So yeah, so you have already did all your learning on your training data. So now you're predicting on training data, and this is actually not a good idea. The reason is simple is what exercise you would do on class, you should not do this when you're actually going to exam, right? Because you already learned it. So that's why what we do, we usually separate training data with test data. That's why if you look at that, we actually have a separate CSV for testing. So one thing you can do, but the issue with that is Kaggle doesn't provide any actual value for test data. So there's no survive column in here. So you can predict, but you don't know how good is your prediction because Kaggle didn't provide it. But what you can do, you can split. So before training, what you can do, let's rename it to something else. Yeah. So we'll split into our own version of train and test. So from scikit-learn train and test. That's a train test. Model selection. Okay. Train test split. Okay, so this is the method. If you do train test split, if you do train and risk df, and then you have to specify the test size. So what it does, it takes whatever train data you have, it is split into training set and a test set. And so now you have two different training and test. So the test size. So usually what people do, 80% of the data, usually people use it for your training, and the rest of the 20% is for testing. So you can also say like 0.1, that means 90% of your data will be used for training, the rest of it will be used for testing. Okay, train. So let's just rename it into train and it's the df. And here, so what we have done, we have trained our algorithm on 80% of the data. Or so
what did you just do to that chunk?
which chunk?
The one that was
This?
train underscore df, was that?
This?
Yeah.
Oh, sorry. Yeah, I just renamed it. Yeah, sorry. Yeah, it's sometimes very hard to keep track of things. Okay, so yeah, we have trained, yeah. And now, so we have trained our algorithm on training data that was 90%, and we can test it. But before testing, what do you have to do? You have to do the same transformation we have done on testing data, right? You have to do the same transformation. So data frame mapper, we have to do the same transformation in test. So test. We do the same transformation on test. And then now, okay, so now we can, so yeah, this is the data on it on test. So now if you want to see the accuracy, learn accuracy. Why true, why predicted. Okay, let's see the accuracy. It's the function that will give you accuracy score. is what's been predicted. This is where okay, we got 84% accuracy. So as I said, linear classifier will take you a long way. Okay, yeah, I guess that's it. I wanted to cover a lot more things, but yeah.
We can post on to the book. Anyone have last questions?
Oh, yeah, sorry, any questions?
Yeah, some questions before.
I guess what's really going on behind the scenes for this scikit-learning thing, and like, do they actually have a equation or something?
Equation?
Like, in terms of explainability, when you show this model to somebody else and then they question whether they can use it?
Yes, you can actually see. You can see this is a decision function. Sorry. Does it take? Never mind. Actually, see. Class. These are the coefficient for the linear function.
Those are each of the features?
Hmm?
So those are each of the features?
Yes.
Like the coefficient?
Yes. Yeah, so this is the coefficient for the linear function. Yeah, and also by looking at the coefficient, you can know which feature is more important, which feature is less. So if the value is greater, it's more important. If the value is lower, it's less important.